speaker is Gabriele Travaglini from Queen Mary.
Okay, thank you very much.
Amplitudes to Wilson loops.
Yes, there is also, so then just first a disclaimer, as Michael Green's talk last 2 days ago, this is a blunt recycling of a seminar I gave last week at Cavendish. Yeah, let's see. It's a very old laptop, so. But I did change the first slide, so I changed the title. Now it's called From Amplitudes to Wilson Loops. Not because we really understand the connection between these two things, but because I really would like to get to the end of the seminar, which is about Wilson loops. Okay, so that is a brief, okay, first I should say, this is work done at Queen Mary with my collaborators Andreas Brandhuber, Bill Spence, and then with two postdocs, Kostas Zubos and Paul Heslop. Okay, so outline of the talk. First I will give you a brief review of amplitudes, the status of our understanding of amplitudes in gauge theory and gravity, and specifically I will talk about some recent progress done in the calculation of non-supersymmetric amplitudes in Young mills within the MHV diagram method, and this was kind of a puzzling problem for a long time, and now we start understanding how things work. But I would like to converge kind of fast on the last point of the seminar, which might be more interesting for this audience, which is this, which was motivated by this very nice paper by Aldair and Maldacena, which addressed the calculation of scattering amplitudes from string theory. And as many of you probably know, the calculation turned out to be the same as the calculation of a Wilson loop in string theory. And we did a calculation of weak coupling, so perturbative gauge theory, and the result, very surprisingly, again, seems to give us MHV scattering amplitude in n equal 4 super Young mills. And field theory, we don't really understand why this is so. This is a completely open question. So this I would like to talk at the end. And again, this is really informal, so we can ask, please, many questions. Ask many questions as you want. Okay, so the main idea is that we know that scattering amplitudes are extremely simple, but if you try to compute them with Feynman diagrams, the intermediate steps are extremely complicated. So somehow we don't really know why they are. We didn't really know why they are simple, and now we start understanding why. After the very important paper by Witten in 2003, Witten introduced the notion of twistor space applied to amplitudes. If you transform the amplitudes to Penrose's twistor space, you see that they have a very specific geometry. They are localized on certain simple curves. So we understand now the simplicity of these amplitudes in terms of the simplicity of these curves in twistor space. The other very important point is that in all of the seminar we will be talking about amplitudes that is gauge invariant and on-shell quantities. This is the root of the simplicity. We never talk about things which are off-shell. So the complication that you would find by doing a calculation with Feynman diagrams is that separately the diagrams are not gauge invariant, and this gives a lot of troubles. So just stated again, the simplicity of the scattering amplitude is completely hidden in general by Feynman diagrams. And all the new methods which have been developed, on the one hand they incorporate this simplicity, like the MHV diagram method, which really reflects the geometry of twistor space, and also, and perhaps more importantly, they allow for very efficient calculations, which are really important because what we are addressing here is really even QCD. So things which are, these amplitudes are going to be used concretely in the colliders. Okay, so let's see some numbers. So if you want to calculate a scattering of two gluons into n gluons, so what would be an n plus 2 green function, if you wish. So if you have 4-point process, you have 4 diagrams, then you see 5, 25, and then these numbers, they start growing very fast. This is a factorial growth. Nevertheless, the result sometimes is extremely simple. So, for example, we know this infinite sequence of scattering amplitudes of gluons at tree level. So these are gluons where all the helicity is the same, or all the helicity is but 1, and the result is 0. So you sum all these incredible numbers of diagrams, and you get 0. And you don't really know why. The other major example is this other very well-known infinite sequence of amplitudes. These are the MH3 amplitudes, or maximally helicity violating. They are called this way because these are the first non-vanishing amplitudes at tree level. And Parker and Taylor conjectured this very beautiful formula, and I will explain these symbols later. And this is also extremely simple and comes from summing this enormous number of diagrams. The other point is that when you really perform, let's say you do an endpoint calculation and then you want to do an n+1, you really have to do a calculation from scratch with Feynman diagrams. You cannot recycle much. So somehow we were missing something about the structure of these amplitudes. Okay, so this is how, that's a transparency stolen from Silver. This is a real calculation. It's a piece of a 5-point amplitude at tree level. So if you would zoom in each of these little terms, you would see 5 polarization vectors. Again, you have to imagine that you sum them up and you get 0, something extremely simple. Okay, that's just a short list of some of the new techniques which are by now available. At tree level, one of the most amazing results is this recursion relation by Brito, Cacciato, and Feng, later proved by Brito, Cacciato, Feng, and Witten, which I will discuss a little later, actually. And then MH3 diagram method, which will be one of the topics of this seminar, where we will see that MH3 scattering amplitudes are lifted to full vertices and joined with scalar propagators to a new perturbative to give a new perturbative expansion of Yang-Mills theory. And I will talk specifically about loop diagrams and about application of this to non-supersymmetric Yang-Mills. Some other very important advances are some new form of unitarity. So we knew very well unitarity of two-particle cuts that was used a lot by Byrne, Dixon, Dunbar, and Kosover. But one can do better. One can cut more propagators doing generalized unitarity, which is actually a very old idea. It already appears in the 60s in the analytic S-matrix book. And this is extremely powerful, especially in N=4 super Yang-Mills. It basically allows you to calculate one-loop amplitudes by just gluing tree-level amplitudes, so no loops whatsoever. So N=4 at one loop is an algebraic problem. This we probably won't have time to discuss today. And there are also applications of this technique to theories with less supersymmetry, and in particular to non-supersymmetric theories, which give you extremely fast ways to compute amplitudes. But let me start. I really think that this recursion relation is quite fundamental, and also it's extremely simple, something which could have been probably discovered 40 years ago. So I would like to just say something about that. So first of all, it's a recursion relation which applies to three-level amplitudes, and it needs the notion of complexification of the momenta. So you need to go to complexified Minkowski space if you want to discover it. And there are only very few things you need to know in order to apply this recursion relation. So the first point is you need to know factorization of three-level amplitudes. So basically, you can also try to derive it directly from Feynman diagrams. You fix certain propagator in your Feynman diagrams, and you want to know what happens when the momentum of this propagator is going on shell. And we know what happens precisely. So you take one three-level amplitude here, and you take a sum of certain number of momenta p going on shell, and you know that this factorizes in the product of two other amplitudes with propagator in between, 1 over p squared. So there is a divergence, and this is basically the residue of the divergence, the product of these two three-level amplitudes. So it's got a bilinear structure. This recursion relation has a bilinear structure which is inherited by this factorization over here. And it's
all
yes?
propagators you're thinking of are massless?
Not really. So that's another one of the powerful things of this recursion relation. So this factorization here is true always. So even for massive theories, this will be true. There are some technical requirements which I will mention later, which you need to check. But in general, you can apply it also to massive particles.
It's you have to go on shell then.
Sorry?
Center.
Yeah, there will be 1 over p squared minus m squared, of course. But the explicit form of the recursion is a little less nice. So it becomes particularly nice when you can use the spin-helicity formalism for massless particles. But still you can, and there are many papers, so in the seminar I gave last week in Cavendish, they were particularly interested in this. So they are planning to code this recursion relation for massive particles and apply it to three-level processes in QCD and so on. That was the point which I discussed more. The second input is the following. So when you start decomposing this amplitude more and more times, of course you get the building blocks becomes amplitude with a smaller number of particles. The smallest building block is going to be a 3-point amplitude. So now these objects usually vanish. You have 3-point amplitudes of massless particles. In real Minkowski they are 0. But if you complexify, they're not 0. And there are only two possibilities. You can have 2 minus and 1 plus, or 2 plus and 1 minus. These are the only cases you can have. So this is MH3 and this is anti-MH3. So they are extremely simple. They are given by this Park-Taylor formula for the case of Young-Mills. So they are extremely compact. And plus you need to know propagators. So eventually when you apply this recursion relation several times, that's what you need to know. Just these two things. And the very interesting thing is that you can of course calculate this by using Feynman rules, but because these objects are holomorphic or anti-holomorphic in terms of spinor variables, it turns out that you don't really need to calculate them with Feynman diagrams. You can just use something I will show you later called auxiliary relation, which basically it's a relation which tells you the scaling of the spinors, which is implied by polarization vectors. So you can just fix it by symmetries. So somehow up to here, the message is that if you want to calculate 3-level scattering amplitudes or your 3-level S matrix in Young-Mills, you can do it without looking at Feynman diagrams. There's one important technical requirement for this recursion relation to work. So basically, what's going on here is that okay, I can say this in words. You want to make sure that your scattering amplitude is just a sum of simple poles without no constant term. So somehow you want to make sure that your amplitudes go to 0 fast enough at infinity when you perform certain deformation of your momenta. That's a bit technical. I don't want to really enter in this into this, but that's a single requirement that you need. So you shift somehow your external momenta, some of your external momenta, and you want to make sure that the amplitude goes to 0 at infinity.
Excuse me, can I just ask,
yes.
You said, is this supposed to be true for any gauge group?
Yes. What is really applied to are the so-called color-ordered partial amplitudes. But in the next slide I will talk about gravity. Yes. So with the color-ordered partial amplitudes, you strip off the color.
I don't understand that. The
color-ordered partial amplitudes, where you write at 3-level, you write your amplitudes as a single trace times.
That sounds as if you're using SUN or specific.
If you wish, but this is. I think you can do this even. You could probably do it even if you leave the color factor inside. It might be more complicated to.
Is it true for E7, for example?
Can you still write it as a single trace? Probably yes, because it's planar. So I think it would be still true.
Not in the fundamental.
Sorry?
Not in the fundamental. That's the. When you write a trace, you really think of that as inline matrices.
Mm-hmm.
There's no sense of planar for E7. Right.
Yeah, okay, still. Anyway, now I want to talk about also. I want to mention something non-planar, so gravity. So gravity also, in gravity, these inputs of this recursion relation was basically factorization. That's true also in gravity, perfectly true. So you may think that this recursion relation should also exist there, and in fact it exists. Now the really interesting thing is that if you try to check this large complex momentum behavior, so as I said, you need to know that these requirements of vanishing of the amplitudes at large complex momenta is satisfied. You do in Young-Mills, you can check it by using Feynman diagrams. It's a very simple exercise. You do it in gravity, it doesn't seem to work because the square root, when you expand the square root, you get a lot of momenta. The nice thing is that actually it works, So the recursion relation still holds, although from Feynman diagrams it doesn't seem to work. And in a very interesting paper, recent paper by Burr and collaborators, this is quite a surprising large complex momentum behavior was related to the better behavior of loop amplitudes. So somehow, Burr and collaborators, they believe that if n equal h square gravity is going to be finite, the root of this finiteness has to be found in this very benign large momentum behavior at 3 level. So something which is not related to supersymmetry, which is quite interesting. So they are able to, by using cuts, they are able to relate this large momentum behavior at 3 level to the absence of certain functions in the loop expansion of the amplitude, which would make the amplitude at some point divergent. So that's very interesting.
Can you just amplify this simple Feynman calculation to show that at complex momenta it does go, the amplitudes are zero? I'm not sure what you're actually wanting someone to verify.
Okay, that's actually important. One part of this seminar on non-supersymmetric amplitudes was actually given by Kostas Zubos here some time ago. So since I want to go to Wilson loop, if I spend more time here, then I will feel that I can skip other things later. But this is a really important point. So what I mean, what you really want to do, so you take your amplitude, say an endpoint amplitude, some legs 1, 2, up to n. So the recursion relation starts in this way. So you want to, so if you consider this as a complex function of many kinematic invariants, which you can also make complex, it's still complicated because complex analysis in many complex variables is complicated. So the idea is to define a complex function of one single variable. Okay, so what Brito, Kachazon, Feng, and Witten did is the following. So you select, let's say, two special momenta, so you're going to treat them in a special way. So let's say I'm going to select pk and pl. Okay, what I do, I shift them. Can you see here? So what you do, I define a shifted momentum pk hat function of z. So z is a complex variable. And I say this is pk plus z times some shift eta. And I shift the other momentum pl in the opposite direction so that momentum conservation is maintained. So what I want to do, I want to define a one parameter family of scattering amplitudes, which I'm going to call A of z, which is the scattering amplitude I started with, all the momenta unshifted except these two. So I'm going to replace them. So I want P1, P2, then I will have Pk of z, and we have Pl of z up to the end. So of course, since what I want to, what they did is to show that this one parameter family of scattering amplitudes has only simple poles, and they want to relate the residue to the factorization, to this nice picture there. Okay, so you want to make sure that these two guys are on shell for any value of z. So that means that you have to impose certain condition here on the momenta. If these are, so one very convenient choice is to take eta null, and then you can try to, so you write p hat square k of z equal to p hat square l of z equal to 0, and you want this to be 0 for all z, and then you find that pk dot eta must be equal to pl dot eta and should be equal to 0. And then you solve for eta. Now, in real Minkowski, there is no solution for this equation, but there is in complex Minkowski. There are two solutions which are, there are two solutions for eta, which are the spin or lambda for particle k, spin or lambda tilde for particle L, or vice versa. Okay, so now what you really want to, so that's why you have to introduce complex Minkowski. Otherwise, you don't have a solution for this thing. So the next thing you want to prove, so you want to prove that A of z is a sum over, say, over k of certain residue ck over z minus zk. and you want to make sure that there is no constant term here. Let's say A0. You want to make sure that this is 0, because I can predict the residues, but I don't know how to predict this number. So I want to ensure that A of z goes to 0 when z goes to infinity. Okay, this I can ensure if I pick this shift in an appropriate way. So what I have to make sure is that I can prove before starting this calculation by inspecting Feynman diagrams, so whatever other mean I have to make sure that I know that this condition is satisfied. And so what I do, then I really start considering all my diagrams.
Raise that.
Just don't see the razor. Oh, I can raise this.
No, the board behind, just lift it.
Ah, okay.
The erasers.
Yeah,
This
underneath
one?
your computer.
No, this one.
Just push that up.
Okay, so I can. So I have these particles K and L which are shifted. So I start looking at all Feynman diagrams which contribute to my amplitude with this shift in place. So I would have something like, I'm just drawing something random. And I have K and I have L which are shifted, so they depend on Z. So how does the Z dependence enter such a diagram? So it enters through all the propagators which are in between these two legs, but not outside, of course. It enters through the vertices, which I have here, and finally it enters through the polarization vectors here and there. So what I can, so the vertices, quartic vertices, we don't care about them, they're constant. The trivalent vertices, they contain 1 power of momentum, so they contribute 1 power of of Z, of this shift. You can see that easily. And you can also see that each propagator contributes 1 negative power of Z. So all in all, if you just sum vertices and propagators, you find Z. Okay, this you can see very easily. So that's still not enough, but we still have these polarization vectors here. So you can prove that there are certain nice, I will show these polarization vectors later. So there are some choices of the elicities of this particle K and L, which guarantee you that for each polarization vector you get 1 over Z and another 1 over Z. Okay, so we get 1 over Z. Again, it turns out that there are more choices than those we can predict by this argument. So again, even Young-Mills estimate based on Feynman diagrams is not really good. In gravity, you try this, you fail miserably because the vertices give you a lot of powers of momenta. Nevertheless, it's still true. So there are a lot of cancellations going on. So that's the explanation. But it's really, really fascinating. What I find fascinating is the simplicity of this recursion relation. Okay, so basically what I'm saying is that by also knowing this expression of the 3-point vertices, which you obtain by decomposing your amplitude many times, you run the recursion relation, you can calculate any 3-level amplitude in Young-Mills and gravity without really looking at the Feynman rules, which is really good because even the 3-point vertex contains 171 terms. That's this famous paper by De Witt. And again, the result of this, if you would really sum this thing, you would obtain these very simple expressions. So it's really a big advantage to.
So I guess my way of viewing all of this these days is Paul Manfield's stuff, where he actually does it at the Lagrangian level.
Okay.
And makes a transformation. Can you do that for the gravity stuff as well? Or?
So Paul did that for MH3 rules. So that's a slightly different thing. This is so there you really sum over all possible diagrams. These recursive diagrams are slightly different. So there is no really we don't really have a Lagrangian formulation of this recursion relation. But to answer your question, there is a paper by Tyson and friends, and many other papers also of other people, including David Dunbar and collaborators in Cambridge, and myself and my student Queen Mary, where we try to write down MH3 rules for gravity, and they work, but they are less easy to use than MH3 rules of Young-Mills. So you can do that, but it's less practical. Okay, this is for those who I wanted to anticipate this here. This is this auxiliary relation that any scattering amplitude of a massless particle of any spin satisfies. These are the spinors associated to the external momenta. So it's probably a very well-known fact. I read it for the first time in papers by Witten in 2003. But if you use this expression plus the fact that 3-point amplitude are either holomorphic or anti-holomorphic, so only one of these two terms contributes, you can completely fix the expression of the 3-point amplitude. So this is what I was saying before. Even for the 3-point amplitude, you don't need to do a calculation based on Feynman rules. Yes. Sorry about that. So what we tried, we didn't publish that, but there is a paper by Freddy Cacciaso and collaborators. We and them tried to study recursion relations for particles of higher spin, because not much is known about particles of higher spin. And it turns out that if you, for example, try spin 3, so you determine the 3-point amplitude in this way, that's going to be the power S. So S is the spin of the Yang-Mills 3-point amplitude. Then you try to run this recursion relation, you find inconsistencies. You find your results are not correct, which is kind of nice because we know that there are no consistent theories of particles of a certain higher spin alone. You need something more. So this could be a tool. The idea was to try to use this recursion relation to find consistent matter content for theories of higher spin. That's a new way to attack this problem. Okay, now I go back to something more fundamental. So if you want to study amplitudes in Yang-Mills, people of course knew for many, many years that these amplitudes are very simple and that the way we describe them is not very efficient. So there were two very important tools which were introduced. One is choral decomposition, and the other one is spin-on-helicity formalism, which I'm going to review very, very briefly because probably many people know already what is this about. So choral decomposition is what I was saying before. You take scattering amplitude at 3 level in Yang-Mills, and since 3 level Yang-Mills is planar, you can write them as a single trace times another amplitude here, and you see that the trace as an ordering here, so this amplitude also has a cyclic ordering inherited by this trace, from this trace. And the nice thing is that here, inside this so-called color ordered partial amplitudes, there is no color whatsoever. So the goal achieved in this way is that to disentangle completely the color. So these objects are simpler. And they're simpler not only because color is not there, also for other reasons. Since these objects have a cyclic ordering inherited from the trace, even if you want to calculate them from Feynman diagrams, you have to include less diagrams, only those which have a cyclic ordering of the external legs. And also the analytic structure is simpler because for the same reason they will depend only on a subset of all possible kinematic invariants, namely those which are made of sums of cyclically adjacent momenta. Okay, so that's much simpler to calculate. You have more of them to calculate, but each of them is separately simpler. And now if you want to, of course, if you want to go to loop level, there will be multi-trace contributions, but you can say, first you can work in the large n limit, and then this is still going to be the leading term. And plus, for example, Byrne-Dixon, I think Dunbar and Kosover have proved that beyond that, the double trace contribution can written down as a combination of these color ordered amplitudes. So it turns out that actually the knowledge of this object is enough. Okay, but this is what we will focus from now on, these color ordered amplitudes. So second ingredient, this applies specifically to massless particles. This is great simplification of massless particles is because we can introduce a spin-on-helicity formalism. That's the idea. So you take a vector, actually you can take any vector in this case, and you just rewrite this as a 2x2 matrix by dotting it with Pauli matrices. And in particular, if P is null, so P squared is 0, then the determinant of P is 0, which means that this matrix has not rank 2 but less, and you can decompose it in this way. So lambda A and lambda twiddle A dot are two spinors with opposite helicity, say 1/2 and -1/2. And so we have achieved this decomposition, this is one of the most important formula you can see in the field. This is the root of many of the simplifications that occur. And these are just some symbols which appear everywhere. These are the two Lorentz invariant inner products you can write down with spinors of the same helicity, so lambdas and here the lambda twiddles, and we use two different symbols, one angled bracket and one is a square bracket. An important fact is that if you want to know the dot product of two vectors, this is just expressed in terms of the product of these two brackets of different kind. Okay, so now the idea is that we want to eliminate moment and polarization vectors in favor of these spinors. And we can do that because also the polarization vectors or tensors, or say in general the wave functions, can be expressed in terms of spinors, of the spinors which define the momentum of the massless particle. So for example, if you have gluons with plus and negative helicity, these are the expressions of the polarization vectors for plus and minus helicity. Here eta and eta twiddle are two reference spinors, but you can easily show that the expression of these two polarization vectors is actually independent of the choice of these spinors up to gauge transformations. So the idea is that from now on we forget about momenta, forget about polarization vectors, and only use spinors and helicities, which are the right degrees of freedom for massless particles. And it is in this description so that suddenly you can at least see the simplicity of the amplitudes, although still we cannot explain it. Okay, so in this setup you can easily see that these amplitudes are actually zero, and you can also see the beauty and the simplicity of this Park-Taylor formula. So this is the infinite sequence of scattering amplitudes of gluons at tree level, all of which have positive helicity except two. So here I and j which have negative helicity. And it was kind of nice that when 1986 Park and Taylor conjectured this formula on the basis of some examples, 4 and 5 points that they had, they concluded their paper saying that they challenged string theories to prove that this result was correct. I find this pretty interesting. Okay, so far I mentioned the amplitudes at tree level, but the nice thing is that simplicity persists also at loop level. So that's the simplest loop level amplitude you can imagine. So that's an endpoint, so again an infinite sequence. This is also quite remarkable because usually we don't have infinite sequences of amplitudes. So the endpoint MH3 amplitude in the simplest possible theory, which turns out to be n equal 4 Swing and Mills, at one loop. So the result of this amplitude is, first of all, it's proportional to the tree level amplitude, which contains these spinors here, this spinor factor, times a sum of so-called two mass easy box functions, all with coefficient 1. So these are very simple functions that Michael Green also showed last day. And the specific character of this function is that the two opposite legs, here small p and small q, are massless, and these other legs here and there, capital P, capital Q, are massive. So these are very specific box functions. And the other interesting point about this result is that all the coefficients here are equal to 1. So I will tell you at the end, hopefully soon, that we can understand this once, because basically what happens is that these box functions are nothing but Wilson loop diagrams. So each box function is precisely the Wilson loop diagram, so the one is just understood because we sum over diagrams. And this amplitude has a long history. It was calculated for the first time by Byrne, Dixon, Dammer, and Kosover using unitarity, and we also re-derived it in 2004 using MH3 diagrams at the loop level, which was quite an expected result at the time. And now recently it appeared again using these Wilson loop calculations. And of course this is the subject of a very interesting conjecture by Byrne, Dixon, and Smirnov. So there is a all loop conjecture of these people for the same amplitude, which has this form. Probably many people here have seen it already. So basically it's we factor out the tree level amplitude here, so we talk about the remaining function. The remaining function is an exponential. An important point is that here the one loop amplitude appears. So this is the signal of some iterative structure where you can calculate higher loop amplitudes in terms of lower loop amplitudes. And of course these amplitudes are divergent, so they are calculated in dimensional regularization, and here there is parameter epsilon, and here it appears shifted by the number of loops L, and it's multiplied at each loop order by a function fL of epsilon, and the first so this function has three numbers, so because it stops at epsilon squared, and the first number is a very famous object that everyone here knows, a Caspar normal dimension of twist 2 operators, which is calculated so nicely also using integrability. So the important point is that roughly this is exponential of the one loop amplitude. So that's very important point. And by now there are many checks, not many, remarkable checks of this conjecture, 2 and 3 loops, of course, and it also confirmed calculation of the 3 loop scattering amplitude confirmed the result which was obtained by Lipatov and collaborators using the principle of maximal transcendentality for the Caspar normal dimension at 3 loops. And there are also checks beyond 4 points, because somehow the kinematics of 4 points is quite special, so it's very important to go beyond 4 points. And now there are interesting discussions about whether this conjecture of Berne-Dixon-Spinov is actually correct at sufficiently large number of points. Another very interesting factor is the following. It seems that like a new symmetry of n equal 4 Yang-Mills might be emerging from these calculations. It was in this way. So imagine you write down expression of your amplitude in terms of integral functions in dimensional regularization. And then what you do is the following. You take your external kinematics and you make it off shell. If you do this, suddenly you lose all the infrared divergences. You are basically switching to a different way of regularizing. Okay, at least on this integral function. So you can set d equal to 4. Then what you do, you express all the momenta in terms of dual momenta, or region momenta, the same as Toft introduced, and the same which, of course, appear in the Abdai-Maldacena paper. And what you discover is that these integrals expressed in terms of these new variables, they have a new conformal symmetry which acts not on the original momenta, but on the dual momenta. And this is quite interesting. And there are discussions whether this can actually be used to constrain the expression of this amplitude. And it was indeed used at 5 loops to constrain the basis of integral function which can appear in the... So it was checked at 4 loops that indeed all the integrals appearing were conformal in this sense. And then it was used as an assumption to go beyond 4 and to go to 5 loops and check whether, and try to write down an answers for this. So I will try to say something more about this conformal imbalance later. Yes?
When you go back to this conjecture, does that mean something about an absence of threshold singularities or something? When you say that higher loops just sort of simply...
What does that mean?
So you might expect when you have higher loop amplitudes that
yes?
you sort of have more possible sort of singularities. So
you mean this kind of singularity is limited because...
of the full amplitude. Does that imply some extra...
It does... so the structure of this conjecture actually is given by the exponentiation of the infrared divergences. So there is a specific analytic requirement which has to do with the exponentiation of infrared divergences. Now the really important point, the really new thing of this conjecture is that also the finite parts exponentiate. So if you want to really describe precisely what the conjecture is, it's a conjecture about finite parts. So what you have after you remove the infrared divergent part. So in a sense, yes. So the message is that also the finite parts exponentiate. This is absolutely unexpected. The Wilson loop calculation I will show at the end has the same feature. Wilson loops, usually you expect them to describe correctly, or at least you use them in the equivalent approximation to determine the infrared behavior of amplitudes, to calculate this in a simpler way. And surprise is that also the finite parts actually are reproduced in a very precise way.
What do you mean by new conformal symmetry?
I don't know, dual, I can call it dual. Maybe it's not new, but nobody...
Is it obvious that it's not the same as just the original?
To me, it's absolutely not the same.
That is obvious.
Right.
It's like an integrality on the original variables, expecting that to have conformal symmetry in a linear.
This one is also broken once you go to finite n. The one.
Finite n.
Yeah. So it's a really complicated.
Maybe I should go directly to this last part of the seminar because I see my time is limited. So maybe we have some more time for discussions, if you don't mind. I have to close your eyes for a moment and go directly. Since we are talking about Wilson loops, it's better to talk about Okay, this I should show. All what we are doing, we're just going back in time. We're just using the S matrix. Much better way to calculate. Okay. You can see the slides, of course, are Zumpos for the other things. Okay. As I said, this is a recycled seminar, so.
Just one seminar?
So just one seminar, but okay. Back again. So now we are still talking about N equal 4 super young males. So again, what I said before is that very surprising result that the symmetry amplitudes, the same ones I mentioned until now, appear in this very different context, which is calculation of a Wilson loop in gauge theory, where the contour here is specified in a very precise way, and it's the same that appeared in the Alday-Maldacena paper, which I now describe in 1.5 slides. So the motivation was exactly this calculation of Alday and Maldacena, which succeeded in describing scattering amplitudes using ADS-CFT correspondence, which is a very interesting thing to do. And they found basically that their calculation was the same as the calculation of the area of minimal surface, which ends on a certain light-like contour, which is the one we will use for our Wilson loop calculation, which lives on the boundary of ADS. And the really important observation is that the scattering in ADS occurs when all the kinematic variables, all the pi.pj, are all very large. So in this case, you can use the Grossman approximation, and you can basically do a saddle point approximation in your path integral. So that was really key point. And you immediately see one thing. So you do saddle point approximation, you get an exponential of the classical action. That immediately matches the form of the exponential of the BDS conjecture. So you can, even before starting calculation, you would see that there is something in common. And then what we really have to do, as was mentioned before, you have to introduce certain T-dual variables, which were useful somehow to encode boundary conditions in an inter way. And in terms of these T-dual variables, that's what you obtain. So the P's here, let's look at this picture first. The P's are the momenta of the particles. So I have scattering of n particles, P1 up to Pn. So the sum of the momenta is 0, and each particle is null as null momentum. Then what I do, I introduce the region momenta, the T-dual momenta. So I write each momentum as a difference of two momenta. If you wish, these are the momenta of two adjacent regions, and I write the momentum of this particle as the difference of the momenta of these two regions. That's what's going on here. So now I put all these momenta one after the other. I glue them in this way, and what I obtain is a closed contour because of this condition of conservation of momentum. Okay, so this is the contour of the Wilson loop, and this is expression, of course, of the Wilson loop, which is relevant in n equal 4, omitting the fermions. So you see that, so here the x dot will be the momenta on each part of the contour. So x dot squared is going to be 0. So now if I want this object to be locally supersymmetric, I need to satisfy this condition, x dot squared equal to y dot squared. And now since x dot squared is equal to 0, I can satisfy this by just setting y dot equal to 0. So I'm basically eliminating the scalars. So there are no scalars. From now on, there will be no scalars. So this is a Wilson loop which is made purely of gluons. Okay, so of course, if you want to check whether supersymmetry is maintained, you will discover that in general, each segment preserves a different supersymmetry. So in general, supersymmetry is broken by this Wilson loop. And what we want to do, so Alday and Maldacena calculated this object as strong coupling in the end. So we want to perform the same calculation at weak coupling. And the 4-point case was addressed in a very nice paper by Drummond, Konchevsky, and Sokachev. And they also found that the result agrees perfectly with amplitude. It agrees with the MHV amplitude in n equal 4. So notice Wilson loop doesn't know anything about helicity. There are no helicity in this calculation. And I will show you now the diagrams, and you will see that there's nothing about n equal 4 even at one loop. Beyond, you will start seeing the appearance of n equal 4. So what we did is the same calculation for the n-point case. So n-point case is remember the sum of very precise box functions. So it's an extremely specific kinematic that you have to reproduce, very specific box functions. And we found that these are reproduced very neatly. And as I was saying before, there's a big surprise here because we don't really expect. First, if you are a phenomenologist and you want to calculate certain part of scattering amplitudes, you will never dream of putting your momenta of your particles in this way. You would perhaps put them all in a, say, star configuration. No, that's what you would do. But this is completely unusual. And second, you would not expect to reproduce the whole amplitude. You would expect to reproduce correctly the infrared divergent part of the amplitude and nothing else. So here there is a surprise. And we think that, maybe we hope and we try to check, that this duality actually persists also to higher loops. I will say something about this later, and there are reasons to believe that. And at 4 points and 2 loops, it was checked recently by these people in a paper that this is actually true. Okay, so here is the calculation. It's extremely simple, so it's one of the simplest calculations you can try to do. So this is our Wilson loop, and we want to do 1 loop corrections. So there are actually 3 kinds of diagrams. The first kind of diagram is not written down because it vanishes. It's the case when you stretch self-energy of a gluon here or on any other. So this diagram vanishes immediately because they are proportional to p dot p, where p is null, so that's 0. So you have only these 2 classes of diagrams. So you have diagrams where the gluon stretches across a cusp, or where gluons connect to the 2 non-adjacent edges. Okay, nothing else. So if you remember, maybe one of the earlier slides, the result is written in terms of this box function, which contain an infrared divergent part and finite piece. So it turns out that these 2 parts are neatly separated. These diagrams here, the cusp diagrams, they reproduce the infrared divergent parts, and these diagrams reproduce precisely the finite parts of these box functions, all with coefficient 1. Okay, so there is a very clean separation of these 2 contributions, which is useful because that means that you can calculate these finite parts by setting epsilon of dimensional regularization to 0 immediately. Unfortunately, it would be nice if this was true beyond 1 loop, and it's not. So life is not so easy. Okay, so if you look at the cusp diagrams here, that's the result of this calculation, and this is the typical infrared divergent part of the endpoint amplitudes at 1 loop. So S I plus 1 is the kinematic invariant, which is made of the sum of 2 adjacent momenta summed over all possible momenta. Okay, so these are the momenta. So here they would be P1 and P2, and then you have to sum over all possible pairs of momenta. Diagram B, so this diagram where you join all possible non-adjacent edges, it gives this very nice integral, very simple 2-dimensional integral. And if you calculate it explicitly, you find that this is precisely equal to the finite part of these 2 mass easy box functions which I showed you before. And by the way, this is an expression which was not known before. It's quite interesting that a 4-dimensional integral can be actually calculated by using a 2-dimensional integral. Okay, so each of these diagrams where you connect non-adjacent edges precisely reproduces the finite part of this object here. So I can be more precise. So here there is these 2 opposite edges are little p and little q. These are precisely these 2 massless legs which I mentioned before. So this function has 2 opposite massless legs, whereas the others are massive here, capital P and capital Q. And you see, when I do this, when I calculate these diagrams, I don't really see how many momenta there are here. I'm just sensitive to the sum of these momenta, and that's why I get these 2 bunches of momenta here and there. It's very simple. And this is really a one-to-one correspondence between such diagrams and these box functions. So this somehow explains why they appear with coefficient 1. Okay, that's the, if you really want to see the result, we got a result to all orders in epsilon, dimensional regularization. And if you set epsilon to 0, you get this expression. And this is actually the same form of the same new form of the box function which we obtained in 2004 when we calculated the scattering amplitudes, MHV scattering amplitudes in n equal 4, using MHV diagrams. So that's a new representation. When we got it first time, we thought the result was wrong. Then it turned out it was correct. And this representation is actually simpler than the one which is commonly used in the literature. It contains less number of functions. Only 4 dilogs rather than 5 dilogs and 1 log. So this is the full result for the one loop all orders in epsilon amplitude, which we obtained from this Wilson loop calculation. And this was actually calculated long ago by Michael Green and Schwartz and Brink, and there is precise agreement between these two objects. If you want to go beyond 4 points, so 5 points and beyond, we know from the start that there will be missing diagrams if you want to know the result at all orders in epsilon. So these missing diagrams are, for example, pentagons and so on, which would vanish as epsilon goes to 0, and there is no way to reproduce them from the Wilson loop calculation. So beyond 4 points, we do not expect to reproduce results which are correct to all orders in epsilon. So now what about Hager loops, which is really the interesting question. So there is a very nice result called non-abelian exponentiation theorem, which guarantees you that the vacuum expectation value of the Wilson loop is going to be the exponential of something. And the theorem also tells you how to calculate this something. So on the string side, the reason for exponentiation was the Gross-Mendel approximation. On the field theory side, at weak coupling, the reason is this non-abelian exponentiation theorem. And of course, you want to make sure that the exponent is precisely what you expect from from the BDS conjecture, from the Bern-Dixon-Smirnov conjecture. Okay, so the idea is that we want to calculate these numbers. Okay, and we conjecture that this calculation of the Wilson loop will in the end reproduce the amplitude. That's our present guess. And okay, now I want to say a few words again on this dual conformal invariance. It's been argued that you can actually fix the form of the scattering amplitude if you conjecture that when you express it in terms of these dual variables, you have a conformal invariance acting on these dual variables. So the way to prove it, to prove this conjecture, to substantiate this conjecture, is to link the infrared divergent part with the finite parts of the amplitude. So separately they would not be invariant under this transformation, only together they would be. So now the point is that in this way you would be able to fix anything which does not depend on something which is specifically conformal invariant, so cross ratios. And it turns out that you cannot write down any non-vanishing cross ratio up to 5 points. So only after 5 points you can start writing down certain cross ratios which do not vanish. They can vanish because of the specific constraints that we have. For example, we have S12, sorry, we have x1 minus x2, that would be equal to p1. So p1 squared is 0. So if you write down something which depends on this, that would vanish. So only when you have sufficiently large number of points, namely more than 5, you can write down functions which would not be determined by this conformal invariance. But I have to caution you very seriously, that's some result which we obtain. We know that Lance Dixon obtained, and maybe other people, maybe Radu and I don't know, other people. So if you really try to do this, so you could imagine to do the following. You take the expression of the amplitude as you calculate it from unitarity or any other method. So it's expressed in terms of certain integral functions, and then you do specifically what this proposal tells you. So you make your external kinematics off shell, and you replace momenta with this dual momenta. So now what you can do is to try to determine, you can extract the anomalous dimension of the Caspar anomalous dimension from this new set of integral functions, which are much nicer and much easier to evaluate because they are finite. If you do this in practice, you get wrong results. So, quite wrong, yes. Transcendent, sorry?
The lower loop, I mean.
We went up to 3 loops.
3 loops, yeah.
So 2 loops, if I remember correctly, is off by a factor of 2.
Oh, even 2
But
loops.
3 loops, yeah, but 3 loops is completely off.
You should get
So-
some 11 and you don't.
Some, yeah, 11 you don't
So
fudge.
it doesn't even rapidly flow.
No, but somehow it's very puzzling because it's a nice way of trying to constrain the amplitudes. But if you really think about that, there is no reason why this should work, because I take an amplitude, calculate it with my dimensional regularization, and then I suddenly perform this operation on the integrals. I make them on shell, and then I remove regularization. I can miss many contributions in this way. It's not uniquely defined, this prescription. No, so I'm not sure. I think it's a very interesting point to think about, but there is evidence that somehow there is something not really correct about this. But certainly it's very interesting. I don't know what this is. Okay, last thing I want to mention is other very interesting paper of Alda and Maldacena, where they try to present more checks of this conjecture of Bern, Dixon, and Smirnov. They actually found problems. So what they did is that the following very interesting thing. So they took a very large number of points. But the contour now is a zigzag contour where you are zigzagging in time direction, and then you have 2 space-like directions here, L and T, where you're going up and down in the time-like direction, so that each little segment is null. So this is the same contour we had before, but then overall somehow this contour approximates, is like a space-like Wilson loop. Okay, so then you can use results from Maldacena, just recycle. Okay, and of course you won't get all. The result of this is not going to be completely equal to the result of the space-like Wilson loop. So, but certain features will be correct. This is what they argue. So everything which specifically, when you take what they do, they take T large and compare to L, and the coefficient of T over L. So they claim that this can be estimated correctly, safely. Okay, and this turns, so they have 2 checks, one at stroke coupling, and then they also perform a 2-loop calculation with coupling, which, because of this fact that T is much larger than L, is extremely easy because you discard all the difficult diagrams you can calculate. And they found 2 disagreements. So this coefficient of T over L over here, that's a strong coupling result, should be, I think, 1/4 if you get it from the BDS conjecture by using the strong form of the Kasparov dimension. And at 2 loops also they find a different result. It's really different, 2 loops, because even in transcendentality is not what you would expect. So it's quite surprisingly wrong. Of course, this applies to large number of points. They had checked before that n equal 4 points works nicely. So the question arises, where does this break down? Why? So if you want to start speculating, again, you can think back of this conformal invariance and say that, okay, we saw that 4 is special, 5 is special, and 6 is less special. So maybe 6 is right. So many people are trying to check 6 points for this reason, including.
Sort of like when you try to compute the length of the diagonal of a square by zigzags, you always find 2 instead of square root 2.
Okay, maybe.
Right,
There are certain things which I should say.
It's true,
Yeah. Yeah, if you, let's say you want to, not everything works. You take a straight line, for example, and you start doing zigzag. Okay, and you want to compare the calculation of the Wilson line done with this zigzag thing and to what you would get by just going straight in a space-like direction. These 2 calculations are obviously different because the gluons can see the small cusps. No, they see it, but here what it's argued is that somehow is this, I don't know how to call it, this relation between the 2 opposite sides. Somehow that's the one which is where all this zigzagging is averaged out, not everything. So I don't know. It's a very interesting calculation, but maybe some explicit checks would be really useful. That's why people are working on that.
Clear the caps? Not considered.
Is it clear that the cusps? No, it's not.
Caps.
The cusps.
No. Caps. The things, the zigzags along caps.
No, I didn't hear.
The zigzags along the L direction.
Calculation involves mostly t.
So again, if you do things which just join these two things, I don't think you get anything. But you can try to do sort of cusps stretching from one side to the other. To me, it's not completely clear. You have to think a little bit about that, because you are summing things. So I don't have an answer, but it's really would be interesting to check. Absolutely. The point is that you have to sum series then here, because you have to join these vectors. Okay. Summary. Maybe there is no need of a summary. If I had gone through the other parts, I would have convinced you that we have very efficient methods now to calculate scattering amplitudes, which are important first because we understand better the nature of their simplicity, and also for practical purposes, because we can really produce scattering amplitudes which people at colliders will need, because Coulomb scattering is the main background that we have to understand the new physics. So usually a combination of new techniques is the best way to calculate things. Often you use certain techniques to calculate the part of the amplitude which contain cuts, and other techniques to calculate the rational parts, which are the present important problem. Okay, I didn't talk about MHD diagrams, and also I skipped this. And now I talk about this very surprising result. We have no in field theory. If you are a phenomenologist, you don't. I think you would not really know why there is such an agreement. At least all the people we have tried to ask don't know. And there are, of course, many questions. So if you are a phenomenologist, two important points are produce these rational terms, and maybe even more importantly, to try to find efficient techniques to calculate amplitudes which involve massive particles. So progress on this side has been less fast for obvious reasons. We don't have this spin-orbicity formalism. And now the really important, really interesting thing, which is was the main point of this seminar, was to talk about this Higher loop amplitudes, specifically 90.4, and maybe somehow people maybe tend to confuse solvability with integrability, but maybe there will be a connection in the end with integrability. That would be really interesting. And okay, this is just a very, very short list of questions, and there will be many more. Thank you.
Is it possible to use your technique to calculation of the integral kernel of the BFKL equation?
I don't know, that would be very interesting.
Because in principle we used also analyticity, unitarity many years ago, but only at high energy level.
That would be very interesting. Have you tried to use, so when you calculate these objects, do you also use unitarity?
Of course, it was used many years ago, as 1975. All these approaches.
Given that this was informal,
absolutely,
you've got something
recyclable
in
and
between.
informal.
I mean, would you be happy? Not everyone would need to, but I mean, I suspect the part that you skipped would actually have been of interest to some of us.
Not right now.
No, not now. I mean, after lunch, or I don't know how long you're here for lunch. I mean, let's have a very, very informal.
Oh yeah, that's another seminar. I have to work. Okay, we can talk later, so if you want. But I don't know if many people are interested. Well, these also were kind of all the results, but
there are probably some who would want to.
Well, maybe upstairs on the landing you can collectively decide if you want to.
Yes.
Okay. Well, let's be concrete. 2 o'clock then we'll decide.
I also
well, when we come back after the coffee after lunch, you can.
Well, you organisers clearly aren't.
No. Well. Anyway, more questions. Nothing for now. So after lunch. Okay.